Hello, everybody, and welcome back to my series on how to control a spike robot using PyBricks for FLL competitions. Right now, we're going to start with the most basic thing you need when coding a robot. You need to make it drive straight. You don't want it to turn or to veer to the left or to the right. So that's where PID comes in. PID, it stands for Proportional Integral Derivative Control. It's a method used in control systems, like robots, motors, and stuff, to make something reach and stay at a desired value, called the target angle or the target distance or the set point. Like, for example, if you're controlling a motor to spin at 100 RPM, a PID controller automatically adjusts the power to the motor so that it smoothly reaches 100 RPM and stays there. The controller constantly looks at the error, the difference between what you want and what you have, like the difference between the target and the current. Basically, like target angle minus your current angle. So I've actually already gone and coded a program for this, so I'll just explain it through you got quickly for you guys. And yeah, so basically, I define the motors at the beginning. Also have a stopwatch for it. Start by setting everything to 0 and reset the watch. Then you set your target distance. Just to define it though, you might change it later for something else. Now you also want a minimum speed. You don't want it to go too quick. You don't want it to drive too quickly, too fast, basically, because then it'll make it like jump, and you can just like the robot can move forward too much and not reach its proper distance. This is for the distance control actually, and not the driving straight control. So you don't necessarily need this if you don't care about the distance. You just want to make the robot drive straight. Vice versa, you also have the maximum speed, which is 70 in this case, because I don't want it to go too quickly, or else, again, it might drive too quickly and jump. Um, then you have the KP, KI, and KD. Now this sounds like something weird. Like, what's KP? What's KI? What's KD? Basically, it's PID. KP for the proportional, the I for the integral, and the D for the derivative. The proportional term, or KP, reacts to how big the current error is. And basically, the bigger the error, the stronger the correction. So every time you make a mistake, it fixes it itself. Thing is, if it's too high, then it just overshoots and it oscillates. It's If it's too low, then it's sluggish and doesn't fix it a lot. So you should think of it as how hard you should push right now based on how far off you are. The KI, or the integral term, looks at its past errors, like all the mistakes you've made before, and then adds them up over time. And it basically helps remove any steady state error, like when the system gets close but never quite reaches the target. Thing is, too much KI makes the system unstable and also can cause oscillations or a windup. Basically, um, it causes everything to stack up, and that way it just can calculate how much time has passed since I last made a mistake. You could think of it as how much total error has built up over time that I still need to fix. Now, KI is also pretty like sketchy to work with. It's not the best, so it's always best to leave it like very low. Like this is like a fraction of a fraction of one. And then there's KD. KD is the derivative term, and it basically looks at how fast the error is changing. So between like an error of 16 centimeters or millimeters to 15, that's like a speed of 1 per something. But if it jumps from like 16 millimeters error to 40, that's a very fast jump. And basically, it tells it if should it slow down to make it jump less. Like how quickly is the error changing, and should it slow down to avoid overshooting. Basically, what it does, it predicts where the error is heading and damps the oscillations, and it helps smooth the response. It basically tries to calculate the future errors that you're going to make and fixes them before they happen. Thing is, you have to make them each not be too high, or else it'll all overshoot and make a mess. The integral at the beginning is zero, as is the last time and last error. These two are both part of the derivative. It's the last amount of time since I made an error and the last error I made. This can change for basically. This depends honestly on which motor wheel you're using. So you should probably change this for which robot you're using. For my robot, the wheel diameter is 60 millimeters. Just to factor it in to make it a bit different is 1.075. And with these, I can calculate the distance that I'm driving per each rotation of the wheel. Because the robot doesn't actually have like an accelerometer to tell itself how far is it going, but it can calculate how much the wheel is spinning, and that way it can calculate the circumference of the diameter of the wheel, and through that it can calculate how far it's driving. Now, these are both for the acceleration and deceleration. So basically, we're dividing the full run. Say you want to run 100 uh, millimeters, drive 100 millimeters forward. So dividing part one is zero point 0.2 times the target distance, which is, say, in this case, 100 millimeters. And part three is also zero point 0.2 of target distance. So it's also 20 millimeters. So here's the function to define a function, you just do def and then a name, close brackets, and then if you want, you can put in variables that you can change. So here I'm changing the minimum speed and the target distance, and that way I can just change the speed that it goes to lowest whenever I want. It makes it a lot easier, and to tell it how far I want it to go. This way I don't have to change it manually each time in part of the function. Same thing here in the KP control. I just called it KP control because I was working with only the KP at the time, but honestly, this should be called PID control. And the base speed is basically exactly what it sounds, the speed it starts at. Again, also with the target distance. Now, global basically turns a variable into something that goes everywhere. Global means like if you define a variable inside a function, you can only use it in said function. That's a local variable. A global variable means you can use it in the entire program because you've defined it as global. Makes sense, right? Now, the error equals hub.imu.heading, which sounds like a lot, right? But honestly, the imu.heading is honestly just like the gyro, which is the sensor that's built into the robot that can tell its angle and basically can tell its angle and in space that it currently is at. Also have current time for the watch.time. And here comes the math a little bit, just a little bit, honestly. So the integral equals plus equals is a cool trick you can do, which basically means um, plus error, like integral equals integral plus error. So you can think of it like this. So that thing means integral equals error plus integral. And it's also just an easier way of writing it because you don't want to write each time integral equals error plus integral. So instead, you just type in plus equals. It's just a shortcut. It makes less typing. And then you also redefine it to integral equals integral here, which means integral plus its last error, is the minimum between integral and 100. What this means is that we're never going to go below 100 because if we go below 100, then it's just not going to work. It's not going to, it doesn't have enough power. So it's either integral if it's higher than 100, or if it's lower than 100, or 100. So sorry, 100 is the max, not the minimum. Then dt is the current time minus the last time. So like what time you're at right now, how long have you been driving, and the last time you calculated how long you've been driving. Then if it's smaller than or equal to 0, then derivative equals 0, which is part of the KD. Else derivative equals error minus last error. So the error you made right now, or the error you last made, divided by the dt. Correction. Now, correction is the important part. Correction is where you basically calculate how much you're going to fix yourself each time. So here it's Kp times error plus Ki times the integral plus Kd times derivative. Sounds like a lot. But basically, Kp, Ki, and Kd are all variables you defined right here. They're just different ways to change it. You can change that at any time. It's just there's an optimal thing that you can optimal number for the Kp, Ki, Kd that you can always change. So you do each one multiplied by the error, the integral, and the derivative, and that's the correction that you need to do to fix it to keep it straight. And then you go to last error equals error, last time equals current time, so you can calculate it properly. And then you have the left speed and the right speed. Basically, the speed for each motor, for the left motor and for the right motor, how fast each one should go. So base speed minus correction and plus correction. The reason we're doing it in different directions because the motors are opposite to one another. So if one goes in one direction, the other would have to go in the other direction to make it drive forward and not turn. So return basically, does it get to what it says? It returns a value that you calculated inside the function. So returns left speed, right speed, and correction. See here? Told you we were going to use while trues a lot and ifs. Elifs is like a mutant version of an if. It basically makes it longer. Same with an else. Um, and then here you can calculate the rotations you need to move. Again, this will change a little bit depending on how big your wheel is. This is the important part. Basically, what this says is if your current distance is bigger than or equal to the target distance, meaning if your robot has passed where it should have stopped or is where it should stop, it'll break out of the loop and stop. Now, normally you would also give it a few more things, like if it's bigger than this but smaller than this, then stop. Problem is, this is still Lego. So you give it too many things and it doesn't work. It malfunctions entirely. This is the acceleration and deceleration. Basically, all it does is calculates how fast you should drive in each part of like the part one and part two, how fast you should drive in each part, so it gets the most accurate. But these are for the distance control, which is not what we're here for right now. So left speed, right speed, and correction all equal the PID control. Still KP control. I don't know why. And speed, target distance, basically. And then you just left motor.dc, basically direct current. That way, like the amount of electricity you're putting in through the motor determines the speed of it. So the direct current is left speed, and that direct current is right speed. Then you want to wait a little bit because you don't want to overheat like the brain of the robot because it's still Lego, so it's not very good. So don't let it wait; it's gonna malfunction. Then you print all the data, like the distance, the angle, and the speed. Again, do it when once you leave the loop, so you can print it one last time so you can tell exactly what it is. And then the motors stop. Left motor and right motor dot stop, which are built-in functions to each motor. So that's the whole function, basically. It's defined by def, and you define all these outside of the function. To call the function, as you can see, you just type in the name, drive distance PID, put in the variables you need, and you call the function. It works now. This way you can drive straight into missions, solve them without having to worry about the robot steering or veering to one side and then just making it all inaccurate. This way makes it a lot easier, trust me. I've been using this for quite a while. Thank you for watching, and see you in the next one.